Okay, now we're going to move on to our main speaker host that we're hosting tonight. So we'll probably run a little longer, but hopefully, you enjoy the totality of all the stuff we're bringing you tonight. Also, at the end, stick around to the end because, as always, there's a giveaway. The speaker recommended a door prize book, Resilience of Critical Infrastructure Systems, Emerging Developments and Future Challenges. So we'll be raffling that off afterwards. But tonight, we are very honored to have with us Dr. John Thomas. Dr. Thomas is a scholar in residence with the Engineering Management Program in the School of Engineering and Applied Sciences at the University of Colorado, Boulder. He is passionate about the promise of sustainable and resilient life experiences for our future generations, and as such, his research interests explore at the boundaries of engineering and social sciences to try to understand the dynamic relationships between human resilience, psychological development, and the resilience of complex social, ecological, and technological systems like critical infrastructure supporting community well-being. Dr. Thomas holds both bachelor's and master's degrees in electrical engineering. He has an MBA and a PhD in civil, environmental, and sustainable engineering. So with that, I'm going to hand tonight's presentation over to you, John. You want to share your screen?
All right. Okay, well, thank you so much. It's great to be here. It really is an honor to be able to speak with all of you about a topic that means so much to me, resilience from every perspective. And of course, we're taking a little bit of a social and a systemic kind of perspective here, but as I've worked in this field over the past few years, I just realized more and more we can't leave anything out. Everything is connected, and COVID sure showed us that. My goodness. When we look at things in isolation, we often end up marginalizing the very perspectives and inquiry that we're seeking. So I'm looking forward to give you sort of a bit of a fire hose of a broad introduction to resilience, as myself and colleagues at Arizona State University may sharing these perspectives. I'll also just footnote that resilience engineering and resilience concepts in general are really an emergent science. It's an emergent knowledge base. So currently, in virtually every academic or many academic disciplines across campus, there are publications about resilience, and everyone has their view. This is what it is. This is what it is. And as a result, there's no common baseline of reference point of our understanding yet. I kind of think of resilience as being sort of where sustainability was maybe 10 years ago, where we're just kind of trying to figure it out. Where does this go into academia? How do we apply this in the commercial sector? And what languaging do we use? And how do we begin to interpret that for the common person? So with this in mind, resilience is very much it's not like I have a lock on the view, I guess is a way to say it. So these perspectives, many of them are my own. They're shared by a number of my colleagues. But I want to just go ahead and jump in and let's see, I'm going to share my screen. Okay, all right, okay. So what I started to say is I look back at this title and say, oh my gosh, what a nerdy title. Critical infrastructure resilience. I could have maybe replaced that second line with something kind of catchy phrase like being prepared to be unprepared. And I'll circle back to that, but it's a bit of a conundrum. It's something that we face with trying to understand how complex systems respond in a resilient manner with unanticipated disruptions. And to do that, we're all, those of us colleagues working in the field right now are striving to develop and assemble these concepts and frameworks and trying to get some kind of coherence among our different approaches to resilient science. But let's just start off with critical infrastructure, the first phrase in that characterization, and to acknowledge it. Back in the Obama administration, PPD 21 was issued to essentially galvanize or to try to localize a focus on critical infrastructure resilience. It did not actually implement policy, but it did strive to get the commercial sector working within and among itself, and issued a number of guidelines. And among those was a National Infrastructure Protection Plan. But just to give you an idea of what is critical infrastructure, really the key phrase is it's those products and services essential to public health, safety, and security. That covers a lot of territory. But generally in civil engineering, we're thinking of things like power systems, water treatment plants, transportation systems, communication systems. Here's a list of just a few of those. And I think some of these numbers may be a little outdated, but they're big enough. I think I Googled a couple of them this morning and updated a couple, but it just gives you an idea that it's a very comprehensive network and in a sense, very complex as well. And what is the nuance of this is the interconnectedness and the interdependencies, which are beginning to reveal themselves with issues like COVID that has brought that around. Just real quick, the NIP, National Infrastructure Protection Plan of 2013, issued these guidelines about critical infrastructure resilience. And essentially, this is still used today, a way of organizing critical infrastructure, and identified 16 sectors, specific sectors to sort of organize the approach. But what is uniquely missing here, at least from my perspective and from the work I did in my doctoral research, which frankly this and some of the other documents at the time prompted my research, is the human dimension, is a very specific reference to the human dimension as an aspect of critical infrastructure. After all, where does this stuff come from? Who thought it up? Who built it? And recognizing that the social or the human dimension is intimately connected and a part of critical infrastructure is essential. So that's what we're going to try to touch on here. And I'll just illustrate this briefly. You might recall a couple of years ago, or maybe it's been back in 2018, I think it was, the Flint, Michigan water debacle. They were trying to rechannel water from the Detroit River, and there was just, boy, a real mess of deception and fraud, and it just turned into an awful, awful situation where the pipes were not treated properly to carry the water. The water was diverted. They were trying to save money. In a sense, it just really ended up in a horrendous mess. And, you know, people went to jail. A lot of people got in trouble and things really got shook up. Now, I'm not going to go into this in a lot of detail, but just to highlight the integration and the coupling between social dimension and technical dimension, and the importance of understanding these principles of resilience, of how we navigate these uncertainties, and to recognize that humans are embedded in the design, operation, and maintenance of critical infrastructure systems. So we can't ignore the social dimensions, or what we may refer to as the social systems, the organizations, the companies, the institutions, the policies. Just a couple of years ago, you probably remember the Texas power outage. They were a classic case of being unprepared to be unprepared. Now that sounds kind of silly, but that's exactly what we're up against. And this is another classic example of the way we think about resilience. Typically, in traditional risk science, we use traditional systems theory and statistics. When we think about resilience, we're really addressing those unknown unknowns. Now, we do include things that we're familiar with, but it's generally characterized with those things that we simply don't have maybe we don't have a current mental model of, to even understand what it is that we're up against. And certainly in the Texas power grid, they didn't design this system to be prepared for that kind of weather. And that was on display for the whole country to see. And what we also witnessed here was the cascading effect, the cascading failure. Went from power to water, and then the water trouble and frozen lines and burst pipes and lack of safe drinking water actually became as big or bigger issue in the days after the power failure than the actual power failure itself. So these things can cascade, and one thing can lead to another. If we think about some of the parameters that characterize resilience engineering, we may look at this as sort of a paradigm shift. As I mentioned, if we think about traditional risk management, some of the characterizations, we design systems to be fail-safe. Design it to be really hard, really robust. One of the favorite words we like to hear, design a robust system. And yet what we know is when we design these systems to be fail-safe, what happens? They work really well until they don't, and then they break. And in resilience science, we want to think in terms of how do we make these systems safe to fail? Maybe we can't have the same level of operation as being fully online, but if we still have some degree of viable service or product that's available, and there's a readjustment of the operating or boundary conditions, then that supports this changing or unanticipated condition. And then there's a couple other items on here, for example, going from being very clear and well-defined about what it is that we're looking at and even talking about, and being comfortable with ambiguity and uncertainty. And one of my favorite here, sort of shifting, we tend to, especially we engineers, we like to think in terms of probability. What is the probability that such and such will happen? Well, we kind of turn that on its head a little bit when we think about resilience and suggest, well, okay, we want to think about probability. That is really good to think about, especially with regard to what's happened in the past and those things that we may be familiar with and that we understand. But what is possible? What is actually possible? And that stretches the imagination. And that engages the human condition of anticipation. How might we anticipate uncertainty? How might we anticipate ambiguity? And what might we do to better prepare for those kind of disruptions to our critical infrastructure systems? So Hallnagel et al. In his book, Resilience Engineering in Practice, introduced a very sort of basic definition of resilience, suggesting it's defined by the ability to respond to the actual, monitor the critical, anticipate the potential, and learn from the factual. So these four key elements, and Hallnagel has a wonderful write-up, his fabulous publications, and he really essentially says all four of these elements must be present. And if any one of them is not, then we are not dealing with a resilient system. And another key point is it's shifting the perspective from thinking about, instead of just always looking at what goes wrong, we look at what goes right. Why did that particular system function in the midst of the breakdowns and the other one did not? And it's just a change in approach, a different way of thinking about things. Now, my advisor at Arizona State University and myself and my work, we took Hallnagel's work and sort of extended that. And the four characterizations were changed to sensing, anticipating, adapting, and learning. And this little diagram here suggesting that these are, you may think of them as capacities or elements or properties, stopping short of defining resilience as something that is a specific characteristic, recognizing, like Dave Eisenberg at Naval Postgraduate School reminds me, that resilience is a verb and it's something that happens in response to something else. So as I think Walker said, resilience of what to what. If we just use the word resilience sort of independent, it's like a floating ground. It doesn't have an association and its meaning is somewhat ambiguous. But here we're attempting to ground these particular perspectives, if you will, of sensing. So monitoring system state variables, anticipating, trying to imagine possible state outcomes. And this is where the human condition comes in, because we don't have machines to anticipate. That's something that we bring to the table. And then adapting, so the ability to change these variables to effectively manage the performance in a way that we would like. And then learning, the ability to really differentiate, integrate, apprehend knowledge, and put it into practice. So all four of these essentially impacting and feeding one another, if you will, and recognizing there's some kind of boundary condition within which we're studying at any given time. And then how do we look at the outputs of those conditions, actions, behaviors, artifacts, parameters, all of those kinds of things. So resilience engineering processes, we call them the SOL processes. That's a key part of how the language a number of us at Arizona State University work together on. Now, when we think about resilience and technology, we might ask the question, does resilient technology require resilient people? Well, do resilient people require resilient technology? Well, it's kind of it's a toss-up. We know a lot about this. We know a lot about this, but what we don't know a lot about is that relationship between the two. We have suggestions, and there are certain, there's a lot of work in this field, but there's a lot more work to be done. And so one way of approaching this is using or engaging the SOL processes as a linking mechanism between the human systems and the technical systems, and then try to understand how these things interrelate with one another. What are the interdependencies? How can we know that by making adjustments to one may have impact or making adjustments to another? So as an example of what happens when things go off the rails, you might recall a couple of years ago, the SolarWinds cybersecurity breach, one of the biggest cybersecurity breach in US history. And, hit Homeland Security, Commerce and Tragedy, National Institutes of Health, Department of State, the list goes on and on. Over 18,000 hacks. So here's, again, an example of malicious behavior. The human system, a human condition, is it an individual, a group, a country, whatever, however you characterize that, it's a human system interacting with a very sophisticated technical system. And how do we design our systems to allow for these kinds of uncertainties? These are the big, wicked problems, the kinds of questions that come up in resilience science. Another thing that we face is this notion of transboundary crisis, because whether we're looking at a time element or a physical location or the actual function and the infrastructure itself, among the infrastructure, we know that things can cascade. So using the example of earlier, energy can lead to a problem with water because we need energy to run the pumps. And transportation can lead to problems with everything. So there's all these linkages of how failures can cascade just in the sort of objective criteria of the critical infrastructure itself. But when we think about spatial boundaries and time and lag and how these things work together and overlap, it becomes really very, very wicked. I don't know if there's a way to prime wicked problems to another level, but I should think about that. But I would say wicked prime, going to where all the dimensions are effectively in play. And it becomes very, very difficult to even be able to understand how to approach these things. And oftentimes what happens is we end up playing catch up afterwards and, fighting the fire, so to speak, if you will, but really trying to make amends based on our study of the past versus the ability to sort of engage in the moment and adjust what's needed as the crisis is unfolding. Perfect example. This one hit us all. I mean, my gosh, even as for someone who spends a lot of time thinking about these things, I never imagined that I would experience something like this. And I'm sure many around the world the same way. But when we look at not only through technology and social and commercial sector, the cascading breakdowns and failures of systems and systems of systems and supply chains, it just shows us how vulnerable we really are. And in some ways, it appears we have these very sophisticated systems that are robust and able to endure lots of different types of disruptions. But this tiny little virus just took us down on a global scale. Very humbling. It's very humbling in a professional and in a personal way and an academic way. Lots of lessons to be learned, and of course, this is not done with us yet. We're still going forward. Another example, Deepwater Horizon. When we have conflicting goals, what can happen and how these things can break down. And no one ever anticipated that this kind of breakdown could occur, or that it would cascade to lead to such an environmental disaster that it did. So these are the kinds of situations and circumstances that we're thinking about. And what we recognize is we're effectively trying to negotiate or navigate among or amid human complexity in the context of technological complexity. How do we reason with and find balance between the two? At what point might the human complexity be saturated with the technical complexity? Saturated meaning simply unable to get beyond a particular threshold of comprehension or understanding. Now, I have colleagues that have acknowledged in their view that we have built such complicated critical infrastructure systems with such intimately interwoven interdependencies and interconnections that frankly, in some scales, we don't really know what would happen in certain conditions. And that's a little spooky. That's a little, it's a big uncertainty and it's a big question mark. But just to acknowledge that we can't just look at the technology. I mean, the technology is important. There's a lot of important things we need to understand and work with there. But what is technology? On some level, externalized human logic. We are the ones that created these things. And when we look at the models and we look at the technology, we're looking at some sort of framework of the minds and the people and the value systems of those who created those things. I like to say, for example, imagine this this power station here, someone with all the credentials and all the degrees and the certifications and the training and has operated this, power plant for many, many years. And their routine is they come in and they push, adjust a button, they turn a knob to the right. One day they come in and for reasons not known or understood or anticipated, they turn the knob to the left and bad things happen. Now that's an oversimplification, but the point being that these complex systems that we've created are extremely vulnerable to our human systems. And human systems are largely predictable, but it wasn't that many years ago that not many of us had mental models of people flying airplanes into buildings, for example. What in the world they would ever think that such a thing? And now, of course, we have that different way of thinking. And as such is the types of complex systems that we consider that we're actually dealing with in infrastructure. So as an example, when you think about it, with regard to the human condition, the important thing to reference here is that sometimes we see different things. The predisposition of a particular way of seeing the world, a worldview, or a value system may be different from one person to another. So if you think about it on the most basic level, the way that we perceive information, the way that we interpret problems, and the way we propose solutions is somewhat based on our way of seeing the world and our psychological disposition. And where do we agree and where do we not? And how do we identify those things? And how do we avoid the groupthink of just going along when things appear to be different than what we think they should be. So just as a simple little exercise, for example, and many of you may have seen this before, but just kind of ask yourself, what do you see here? Do you see an old lady or do you see a young lady? You know, it's one or the other, or maybe you see both. But here's the question. Is it possible that two different views can coexist and both be completely valid? Now, in this other image here, we're looking at a cylinder, and imagine projecting a light on the cylinder from the side, and you're going to get, well, if it's cut, you know, at a certain length, either a square or a rectangle shown in the blue here. Well, if you put a light from the tube end, it's going to project a circle on the wall. And if you were only looking at the circle or only looking at the square, would you believe that's all there is? Could you allow for another possibility that doesn't diminish one view over the other? And this is what we're challenged with in resilience engineering, the ability to effectively interpret and perceive multiple different perspectives simultaneously without the need to reduce one in preference over another. Now, that may happen in time, but the starting point is one of allowing for these broader and more diverse perspectives. So in my work, what I addressed was what I call a holistic perspective. And this was came from PPD 21, that presidential policy directive, where President Obama, and the way it was written, the way that document was written, said, "Thou shalt take a holistic approach to critical infrastructure resilience, to the nation's critical infrastructure." And they used this buzz line, holistic, and it even showed up in the NIP, but nobody ever bothered to say, what is that? What is holistic? What exactly does that mean? And here's an example where when simple things like that are not properly defined and left out, then anybody that reads that is going to latch on to their interpretation of what that means. And it may or may not agree with, you know, others. So that's something that, so I approached this and tried, this is one approach to developing a holistic framework for the purpose of trying to be clear about where any given perspective at any given time may be localized. Now, what we're talking about are systems, and the way this diagram is written here typically refers to externalized objective systems, like we think of as traditional, you know, material. We can point to it, we can weigh it, we can observe it, maybe we can measure it. But what we're suggesting here is that there are other perspectives that are valid that contribute to understanding these complex systems. For example, the interior dimension of a group or collective, otherwise maybe think of as culture, shared values, common understanding, shared belief systems. Groups of people interacting with complex systems have some sort of a characterization or amalgamation of these different interior dimensions. And those things contribute to how we interact with and solve and present solutions to problems. And then likewise, the interior individual or the exterior individual, it's really very simple on a sort of a high level, inside, outside, individual, and collective, that all four of these perspectives exist in simultaneity or at the same time. And one does not preclude or diminish the other. It's just at any given time, we may be focused on one over the other. So kind of keep that in mind as we go along, but how do we apply that? So when we think about, when I think about critical infrastructure, first off, I acknowledge that all of the critical infrastructure and all of us humans are embedded in environmental systems. So I could put, you know, the environment around this whole thing, but for the moment, let's think about social and technical, and the coupling between social and technical systems. The same kind of coupling that if I were to hold my telephone, okay, and I interact with my phone, here's the technology, here's the human, and how do I interact? Well, these solid processes is one way to characterize and how to look at that. And this framework gives us an approach to understanding or at least interrogating a broader, more expansive understanding of how these systems interact with one another and how we may interpret the different nuances of their behavior when unanticipated events or unpredicted types of disruptions may occur. And on the right here, we see a diagram that shows, okay, let's consider a power plant and consider how these different perspectives may be brought into consideration. And again, just to illustrate that it's important to understand the technology and the complexity of these systems, but it's also very important that we sort of expand our perspective to allow for the other elements that contribute to our understanding of those systems, and in many cases have influence over. So the brief mention of flying airplanes into buildings, well, that was something that happens in the lower right here. But what we know in the lower left, there was an interiority, a human dimension that had value systems radically different from those of us here in the United States, and it led to, a catastrophe. So this is a way, or one approach, to being able to assure or ensure that we're really trying to bring in all the different elements of perspective and hold them side by side without needing to diminish one over the other. And if we think about, okay, what is the social ecology of this? How is this actually structured? Well, you can go all the way down to, on the physical level, you can even go lower, but it just stopped here at psychological systems, biological systems. But we're humans and we interact in groups and organizations, and we form communities, and there's institutions. And so there's this layer of structure of ecology, all of which are influencing the outcomes and the systems that the very systems that we're studying. Oftentimes, it's like the fish in the water, though. In my view and what I see in my work, oftentimes it's like the fish in the water that doesn't realize it's in the water, and it's studying everything else except itself, and not realizing that it is actually a part and parcel of the very system that it's attempting to understand. And this is what I'm trying to drive home with the emphasis on social systems in relation to technological systems, that we can't ignore them. They're there, and we can include them or not, but it's not like they're just going to go away. This is a resilience main effects model, just to give a framework or sort of a broad overview of understanding. It's a very simplified, even though it looks a little techy. For example, as I mentioned before, the environmental systems are, we're all embedded in the environmental systems, but we're localizing our focus here on the social and the technical, so we could maybe draw a little circle around those two. But this is basically suggesting that, you have an amalgamation of some type of system and different types of systems interacting with one another. And there are protective factors and there are vulnerability factors. And again, this is a simplification. It's adapted from Maston and Luther out of the psychological literature and applied here. But if we have a framework, a boundary condition around something, a region of inquiry, and then that's hit with some kind of stressor, some kind of a shock, could be a hurricane, could be a fire, could be any of a number of different types of catastrophic system failures or disruptions. Then what happens? How do we interpret what works and what doesn't work? And therein it guides us down the path of resilience science. Now, in my work, I striving to find some sort of a linkage between the human dimension and the social dimension. I did a very comprehensive literature search, wrote a paper. It was published in the Journal of Emergency Management and Homeland Security and Emergency Management. And first went to the technology literature and found all the descriptors I could of resilience. What is technical resilience? And what was interesting is, first off, there was no single place you could go to where it says, these are all the things. So that was kind of surprising, but it also points to the emergent nature of the knowledge base. And then I began to recognize, because I did the technical search and I also did a search in the psychological literature, is that there's huge overlap, and essentially a lot of the technical jargon was borrowed and brought right from the psychological literature and then brought into technology. It just hasn't matured in its frameworks and structures and applications yet. If you go into the psychology literature, they're very, very structured. They divide these by cognitive, affective, or emotional and behavioral. And many of them, you can take any one capacity or element, for example, find entire papers and research that's done characterizing these things. We don't have that yet in resilience science. And there's no firm methodology, there's no firm even agreement on a succinct definition. So you'll hear different things depending on who you're talking to. They're starting to overlap more and more, but there's still no firmly agreed upon consistent reference of what that actually is. Now we apply all of that. Why does it matter? What are we going to do? We all know bad things happen. But when bad things happen that we never could have imagined before, and what I suggest to my students to try to really get a grip on what I mean by having no mental model for something, just think about, what is your plan for aliens landing on your lawn? Now, it's a little slapstick intended to be funny, but just to grab you and think, oh, yeah, right. Most of us never really think about that. And chances are, and I certainly don't, even though I use it as an example, have a thought about, well, what would that actually look like? And what could it be? Well, this is what these crises lead us to, these kind of circumstances in situations where we have no mental model to even understand how to approach these things. So in crisis management and crisis leadership, what my work is moving toward is how to develop or bring in resilience concepts and principles and apply them to these different kind of surprise circumstances and catastrophic system failures that we may experience. And that requires, it necessitates a very broad systemic understanding and perspective. It doesn't limit it to that, but it does recognize that there are so many different elements in play that we need to take care that whatever our inquiry may be, that we're including those particular system perspectives that are relevant to the crises at hand. And this becomes a challenge because, again, we don't have, unlike many other sciences, we don't have a template to follow yet. We don't have a process or steps of what we should actually do. We're still discovering that. It's still unfolding. So a very important component are the management systems, the people factor, how we bring that systems thinking into play with regard to relationships within and among employees. We know how critical and how important that is. It doesn't take but one bad relationship and bad things can happen. Somebody comes in and just, all of a sudden, our world is very, very different. Adaptation, the ability to self-adjust, the ability for individuals and groups to self-adjust, to realign according to changing parameters that we didn't have prior information about. So a dynamic sense of adjustment, complexity, and complexity in contrast to complicated, where complexity meaning we have the relationships between all of these elements and not just more elements. And all of these come together with suggesting that management systems are a critical component of critical infrastructure resilience. In fact, engaging systems thinking, and this is something that I bring into the classroom and is really become a lot of people are beating the drum on this one, and systems thinking, and I think systems thinking is very important. I think it's not the end game, but there's three different ways that we suggest a way to look at or interpret what is a system in terms of a dimensional perspective. I can look at a system as in an objective criteria. I can point to it, I can weigh it. That's a thing. is out here. I can look through a system, or maybe I might put the phrase into. And if I can see inside of the system, I see all the nuances and the operating components and the interactions. And last of all, I can look as the system to recognize that no matter what it is that I'm studying, I'm a part of the system of interpreting and understanding that thing. And that's a necessary ingredient. And that's one that is frequently missed when we're looking at critical infrastructure, those products and services essential to public health, safety, and security. We spend a lot of time making sure there's generators and recycling and this sort of thing, but we don't spend as much time thinking about those human factors that can impact how all of those things work. And also about conditions that where maybe we hadn't thought of before. I remember back in 2014, when I just got to Arizona State University, there was a huge storm that came, and there were some generators that got flooded. And it was kind of a bizarre thing. Here we are in the desert, and generators got flooded. And you know, when it came out in the news and the write-up and whatnot, well, no one ever anticipated that it would ever be possible that these generators, where they had been installed, would experience flooding. So that's the kind of ability or system thinking that we want students and colleagues and even organizations to begin to think about, because we can't just look at things in isolation. We got to recognize the linkage and the interdependencies among them, and then discern what is really relevant to the inquiry at hand, and what can responsibly be, you know, perhaps put aside for any given moment. So bringing it around, all around, and now how do we actually apply this, and how do we bring it into a direct practical application? And that under the guise of crisis leadership. The ability or the capacity to recognize, you know, situational analysis, making decisions, communicating on the fly, changing decisions, adapting, prioritizing, and then changing priorities. This is the kind of, there's even an area, I'm not sure if anyone is familiar with this or heard of, adaptive management is starting to come around a little bit more, and mostly applied in environmental science, but the same principles apply, which is it's great to have policy and procedure and guidelines, and sometimes things go off the rails. And the flip side of that is knowing when not to follow the policy and when not to follow the procedure. And that is when we get into this vague, uncertain realm of resilience science. To put it into perspective here, also leadership, and Zelensky and President Zelensky in Ukraine, just extraordinary. I mean, all of us have been, it's very strange that we have this spectator war that's going on now. And if you recall, in the very beginning, what did they do? They attacked the critical infrastructure, trying to knock out the power plants, trying to knock out the water, trying to attack those critical services. And once again, the leadership that come forward, the ability to recognize that leadership can come from anywhere. And it's really the ability to engage and work with things in the moment as they're arising, and to recognize that we don't have specific policy and procedure that's going to guide us through these radical, unanticipated, unpredictable types of events. Who would think that, you know, someone would bomb a nuclear power plant? These are new mental models for us, and there's unfortunate, but we all know there will be new, even more coming forward. So to sum it all up, the irony of resilience is really all about being prepared to be unprepared. And then from there, working with, okay, what do we have? What do we got? What makes sense right now? And how do I iterate my knowledge and my approach and my understanding as new information becomes available, or as dynamics change, such that we can ensure that those products and services essential to public health, safety, and security are indeed available online and here to support our ongoing lives and our concern and our companies and our just ongoing concerns. So that is the very end. That's what I've got for you today. I know I went through that kind of fast. There's a couple of websites here. If you're interested, you can look at some more of my stuff. This part of this research was funded by NSF grant, but it's been continued over the last couple of years. So I'm just acknowledging that here. And with that, I will drop the share and open it up for any questions or comments or feedback of any kind that anyone may have.
Thank you, John. Yeah, folks, feel free to unmute yourselves and shout out your questions that you may have. Or if you find it easier to type something in the chat, do that.
Yeah, so I see a comment here. Yeah, the Texas system was designed that way on purpose, but that doesn't take away what happened or make any of it any different from what it was. And maybe that's one of the sad realities of, yeah, they actually intended to isolate themselves that way and never intended to prepare because they really didn't believe the weather would be that bad. But
well, also
yeah,
they make money by having the system, having the supply go down. So if they take a plant down, then they can charge more for what's available because it's all unregulated in Texas. So there's no incentive to have a standby power plant, because if a standby power plant's not being used, it's losing the owner's money. So they don't build the standby plants. Right. And we have the same problem here in Texas for the oil, gas, petrol industry. 30% of the nation's oil petrochemical industry is here in Houston, but yet we're subject to, if a hurricane comes here just right, you could take out 30% of the nation's capability and have years to replace it. It would crush the whole nation.
Yeah, Steve, you got a question? Do you want to ask it?
Yes, I do. Just I was wondering, you're teaching these concepts, and how do you present them in terms of working exercises and projects, so there's some hands-on recognition of
Sure. Yeah, that's a great question, Steve. Thank you for that. So one of the first things I do, I've introduced two courses here at the University of Colorado, an undergraduate course titled Resilience Engineering Management, and then a graduate course titled Resilience Engineering Leadership in Crises. And in both courses, the students take a semester project. And generally, the semester project is centered around some type of infrastructure, organizational, technological system. And I give criteria and conditions on how to frame that. And then we engage some of the tools put out there by DHS and FEMA for doing a threat analysis. So we start with the characterization of the system itself in terms of social, ecological, and technological, identify the different parameters, try to understand their interdependencies. But really, I use the DHS and FEMA guide to go through this exercise of a threat assessment and then capabilities analysis to recognize what capabilities may be compromised by a particular threat. And then we look at how those capabilities may be shored up or strengthened or addressed. So that's one approach using that. I also use use case studies. I've used the Deepwater Horizon, Katrina, the Waldo Canyon fire here in Colorado, and in each case strive to essentially take one or two of the key elements of how we're addressing resilience and apply them to these very specific conditions. So case studies, I guess, is the short answer to your question, but a variety of different things there.
Josephine, go ahead.
Hi, thank you. I enjoyed your presentation. I would like to know more information about the human factor, if that makes any sense. I think that the disasters that you described all had people that affected the outcomes greatly.
Yeah.
And I just want to know are you doing research? Are there any tools or anything to address the human resilience? People thinking outside the box tend to be successful. One of the things that I'm looking at right now is this Texas storm and the impact that it had on hospitals. And the people were very resilient in the way the pipes did freeze in all the hospitals, by the way, and how they got water to circulate through the hospitals was fascinating. One hospital, they had a pool. They had people taking water out of the pool. Another place had people catching rainwater. Another hospital had people not flushing toilets and were removing waste with garbage bags and everything. It was really fascinating, and no one place did the same thing, right? It was different people coming up with these ideas. So I just want to know, how could we get more examples, or how could we ensure that the human factor would be successful, if that makes any sense? Well, because I think that would affect the outcome.
Yeah, I don't know that I can answer that question. I can only sort of give a marker of where I perceive that to be at this moment. There's a few people like myself who are really integrating the social dimension and paying a lot of attention to that. Frankly, most are not. Most will make a sort of a cursory reference to and characterization, but the focus is principally on the technology or the sort of the technical or the environmental type systems. So at this stage, all I can say is, well, I've got a couple papers out there. There's a couple others that have some papers. I think the work of Dave Woods and Eric Hollnagel has really gone a long way to bring this. It essentially sparked my interest and motivation. I've just dug a little deeper into that social component. But frankly, it's still an untapped knowledge base and yet to be sort of brought into the, so I'm even thinking right now, for example, to teach these courses, what textbooks do we use? There's no resilience engineering textbook. Right. There's only a couple of books that even make enough of a reference that we could even use it in a technical class. Mm. So I'm looking at writing one, or some colleagues of mine are putting one together, but that's obviously going to take time. So I don't have a good answer for you. I wish I did. I can only just point back to, in my experience, resilience knowledge and resilience science, and in particular resilience engineering, is emergent, and it's more or less sort of where sustainability was maybe 8, 10, 12 years ago. And I predict, who knows, knock on wood if I got some wood nearby, but I predict it won't be long before you will see more resilience engineering courses. Eventually, you'll see resilience engineering degrees.
Okay, yes, I agree.
But it's going to take time, and it's going to take those of us in the field to continue beating the drum and continue carrying the torch, if you will. One of the challenges with resilience is that a lot of people think they know what it means, and then they latch onto that thought, and they don't realize that 20 other people had 20 other thoughts about what resilience means. So there's a lack of coherence even among our colleagues and how we approach and what we feel is essential and important. And that's where we need to rein that in somehow, some way initially. But I wish I had a better answer for you.
Well,
but
that's okay.
I'm continuing on.
Your papers in the slides, right? The papers that
if you about. Yes, if you go to
I'll be able to get those.
Yes, you will be able to get those if you go to my websites. When that link is on the very last slide, those papers will be in there. You can find those in there. And I'm not the only one. There's some others as well. So.
Okay, thank you very much. I don't want to take all the time, but it's really fascinating. Thank you.
Thank you very much. Yeah, Rob.
Yeah, Rob.
Oh, hey, Dr. Thomas, thank you for your presentation. A lot of you probably wondering who the heck I am. The reason why I'm here is I work for Dragos Incorporated, cybersecurity firm that's completely built around industrial control systems, operational technology. And the reason I attended this, your briefing was you're followed by Alexandra Scalco at NIWC Naval Information Warfare Center. And she posted this briefing or this webinar on LinkedIn. And that, since I'm responsible for Navy Marine Corps business at Dragos, that's why I'm on the call. Yeah, I'm a little bit out of my league here, but the one thing I do identify with, obviously, is from my perspective, my company's perspective is, because Dragos's motto is protecting civilization. Because in the end of it all,
yeah,
you know, we try to get all the practice we want every year. I live on the coast of Georgia. And every year, June 1st, all the weathermen and everybody talk about being prepared for the hurricane season, because that is nature's way of reminding us of, one, our humility and our vulnerabilities, and two, more people die after the storm than do during the storm. So obviously, from our perspective, from a cybersecurity perspective, that cybersecurity built around industrial control systems, SCADA systems, operational technology is lacking in both the civilian world, commercial world, and Department of Defense, to be honest with you. Because from my perspective, working with leadership within the Navy and the Marine Corps is, if things go sideways in the Pacific Rim, the first attack is going to be a cyber attack, and they're going to go shut down the power. Because I don't care what kind of IT resiliency you have built around cybersecurity, around your IT systems, it doesn't matter if the power goes out, because they're going to go after check. Yeah. So they're going to go after the power, which is disruptive enough. But what about, you know, oil, water, and those types of services? It's the lack of services that cause the biggest disruption. Case in point is the reason why the Russians bombed the nuclear power plant is because they couldn't hack in. And I won't reveal the secrets why. I think you can sense from my tone why they weren't able to hack in, which is why they had to go in by force to take the power plant. And there will probably be more of that. But and again, some of your comments reminded me of what we call on the cybersecurity side, user behavior analytics, the things that are built into to automate a system to learn the behaviors of its users in order to adapt through machine learning to anticipate the usage of a system. However, there's always that unknown. So the other thing is, I just learned that from an OT perspective, the learning curve to get the number of people qualified to build cybersecurity resiliency in critical infrastructure, if we started today, would take 5 years to have enough people qualified to work that, to have that job within that industry to build cyber resiliency in a critical infrastructure system. So, and like the gentleman mentioned earlier with, you know, a hurricane can come in and potentially disrupt, you know, 30% of the oil and gas industry. Well, Colonial Pipeline was a classic example. It was a ransomware attack. You know, that's what it was. So there's things that are happening in this world, and we do threat intelligence through a tool, ironically called Worldview, where we try to anticipate our adversary's behavior and report it to our customers on those operational technology systems that they could potentially have a vulnerability based on some CVEs and some other things that we go out and perform reconnaissance on the network or the World Wide Web and other places to gather that intelligence to feed our users worldwide on, hey, this adversary is active to attack these types of systems. Here's what they're doing, and here's how they went about doing it, and reporting that into our users or our customers. That's what we get worldwide. So, and then for everybody there, I have no financial interest in this whatsoever, but the best book I was told, you probably can't see it. sorry, was Sandworm. And that tells the story about how the whole Russian attack, cybersecurity attack on the Ukrainian power infrastructure came to be, and how a team was built out at NSA to do the protections around it. It's a great read. It's like a spy novel and a whodunit all in the same thing, but it's a really cool read. So
that sounds really
maybe
interesting.
put that in the chat, the
Yes,
title.
sir.
Yeah.
Sure
Yeah,
will. It was recommended to me to read. And if you guys ever get a chance, when it regards to cybersecurity, our CEO, Rob Lee, was the one that built out the team at NSA to do the investigation of that cyber attack on critical infrastructure in Ukraine, and is in an advisory role now outside of the government to the White House, the Obama administration back in the day, DHS, so on and so forth, CISA. So we're very hands-on at the government level, both nationally and worldwide, with other countries to help them develop a plan around critical infrastructure protection from a cyber posture. So again, his name was Rob Lee. And like I said, I'm just here to learn. But if you guys are interested in a cyber perspective on things, look him up. And we got great YouTube content also. So thanks, Doc. I learned a lot. I appreciate it.
Thank you. Thank you very much. And it was great hearing about that. I'm glad someone's really looking closely at those concerns.
Well, it's a lot easier to do bad things with a keyboard now than it is anywhere else, because we can build high fences, we can build physical security all day long, resiliency and redundant systems. But the guy with the keyboard, because everyone thinks that operational technology and infrastructure, critical infrastructure, is in a closed network. And it's guaranteed when we go out and do asset discovery or scan the network, the OT network, there's a Windows box touching it, i.e. SolarWinds. That's exactly how it happened. And it disrupted supply chain. Something that simple, and that's user error. Simple as that.
Awesome.
Well, one of the challenges that we have now is that we really don't have a pipeline in the universities of engineering students coming out with training and knowledge about resilience. So, and yet if you look into the commercial sector, there's, and just Google the word resilience in any job site, and you'll see it's starting to show up in all kinds of descriptions. And sometimes you can even read the description and recognize that the person who wrote it doesn't even understand what they were writing about. But it's one of those conundrums, or those situations where industry has a need, and yet academia has not been able to step up to the plate yet. So we're not producing the knowledge. And so we have a need. Oh, I want somebody who's got 10 years experience in resilience. Like, nobody's been thinking about this. There's nobody even doing it. What do you mean 10 years experience? Be real.
Right.
And so we need to learn how, thinking in a really broad sense, how do we get that pipeline and start working that so we can really begin to build the knowledge base and grow with it while we're addressing these concerns along the way?
Well, Doc, the first thing I think of is someone in your position, and I have a friend of mine I've known for a long time. She's the head of cybersecurity for the graduate program at University of San Diego. And I asked her, when are you going to start up a critical infrastructure cybersecurity program? Well, I didn't think about that. I didn't know. Well, your whole site, your whole data center and everything is worthless if you got no power.
Exactly. Yeah.
So I would call academia to raise the hand and say, hey, because if you look at the National Defense Authorization Act, it clearly states in there that the government has to have, every 90 days, you need to report back to us what you're doing to protect critical infrastructure, period. And there's going to be funding behind that. So academia, because I know that Georgia Tech, Penn State, and I can't remember if MIT is in there, but obviously Idaho National Laboratories, Oak Ridge National Laboratories, those folks are now getting pressure from their customers that they serve, right? Hey, how do we do this OT, industrial control system, critical infrastructure protection thing? They don't have the bandwidth. They don't have the staff to support it. So I would say we need to push it back on academia, saying, what are you guys doing to prepare our future engineers and scientists to start building these systems? Because I think what it's going to come down to, in Rob's opinion, when we start building our own systems, you know, those industrial control systems, those SCADA systems, those things that make it go open and close, until we start building those things ourselves, the threat's always there, right? Because we have no idea where the supply chain, that chip system that's in that SCADA or that ICS system could have a back door and a bad guy in it.
Yep. No, you're exactly right. And you know, one thing, I think a lot of these science fiction movies have done a great job of, you know, imagination about the what if, but it doesn't take much imagination to think, okay, no power 1 week, week 2,
Yep.
week 3, what would 2 months look like?
Yeah.
What about water? I mean, we know that we would go from to civil unrest pretty darn quickly.
Yeah.
And things could get really messy very, very fast. And so I think what some of these events over the last couple of years have shown us is just, it's very humbling to recognize how vulnerable we really are. And how much confidence we have in these systems that serve us. We just expect there's going to be hot water. We flip the switch and we anticipate the power to be there.
Yep.
And yet, if there's no power, I mean, everything, like you said, everything shuts down. Everything shuts down.
Everything.
And so, yeah.
Hey,
Good.
let
Well,
me
thank you.
thank you, Rob, for those questions. Let me take a quick moment to actually thank our speaker with our virtual certificate of thanks here.
Oh, wow. Thank you.
Yes,
Awesome.
I'll be sure to send you a copy of that. Normally, when we do this in person, we actually frame the thing.
Oh, nice.
And present you with framed copy. But yeah,
Thank you so much.
thank you for this great presentation.